Alright, so we've just had quiz 1. We'll have quiz 2 on Friday. Your next homework assignment is due a week from today. Homework 4, which is having to do to precipitation. I'll put that online immediately after class. And we're going to be talking about the hydrologic cycle and maybe get into some initial discussion about precipitation today. So we're kind of transitioning. Previously, so far in the course, we've really been discussing hydraulics. But we're moving more into the basic hydrology. And one of the slides today kind of refreshes the discussion we've had before that distinguishes hydrology and hydraulics and who's responsible for what. But this is going to get a lot less applied and a lot more theoretical, the course. I mean, so far you've already learned some programs that you could put on your resume, and you're not experts at them, but you've seen them enough that you could go out and do some work with them. So, I generally find that students like that. They like learning new skills, new programs. Sometimes they feel a little bit apprehensive when it's getting back into like a fundamental science class. I think it gives you bad flashbacks to freshman and sophomore year when you're just taking a bunch of science. This is an important figure that's in the textbook that differentiates between how we overcome the effects of urbanization, either upstream or downstream. And the basic idea that we often are trying to work towards is reducing the peak flow rate from a storm. Because, of course, when we build a house or put in a parking lot or develop some sort of a structure, what we're doing is we're disturbing the soil and we're increasing the runoff coefficient of that area, because you're adding impervious surfaces like roofs and pavement and walkways, and all of those things that we do is going to make it so that more water runs off of an area than it did in its natural state. And so because of that development, there's now a risk of flooding downstream. And so there's some options that we have to reduce the volume of stormwater that gets downstream, or at the very least delay it. And the source control options are the things that are measures that can be taken to try and prevent the problem rather than manage the problem. You've heard the phrase that an ounce of prevention is worth a pound of cure, and that's absolutely true in stormwater runoff. That if you can improve the infiltration capacity of some area so that the water gets down into the soil, then you're going to save a lot of money and a lot of potential for damage downstream when there is wet weather. And so local disposal options are things that try and increase the capacity of the water to get into the soil rather than running off. So you're trying to lower the C value in order to reduce the runoff volume in local disposal. In the case of inlet control, you're trying to keep the water close to the place where it was generated. And so rather than having one big pond downstream some distance, you're trying to have lots of little ponds, maybe storage under each individual parking lot, for instance. And so that's inlet control, is storage right as it runs off from an area. The first place that it runs off and pools to, you're storing it there rather than allowing it to travel downstream before you would store it. And then on-site detention is maybe the water has traveled some distance, but rather than allowing it to aggregate further, you're either storing it as it travels, maybe a very wide pipe or a flow storage vault in the routing as the water is going downstream. But then once multiple developments have had their flow congregate together, that's when we say that now we're managing the problem rather than preventing it. And so downstream storage are those measures that are more in the thinking of coming up with structural measures to retain the water so that it doesn't cause damage to the environment downstream. So here are some things that you can do to decrease the C value of a parking lot. For instance, if you use permeable pavements that allows the water to travel through it rather than run off. And so the advantage of permeable pavements like this is that The water can get down into the soil, but the disadvantage is that these voids, these interconnected voids, if it's not well drained underneath and water is allowed to pool inside of the concrete, then the freeze-thaw cycle can really do a lot of damage to the concrete. And so these concrete mixes aren't that sophisticated. All you need to do is remove the sand so that you're still having gravel and you're still having cement, but you're removing the fines from the mix, and then that allows these voids to be interconnected. But it's really important to have them on a slope and well-drained gravel underneath so that the pavement itself isn't broken apart by the freezing and thawing. So that's just an illustration of the efforts that we're trying to prevent the effects of urbanization, which inevitably increase the C value and decrease the time of concentration. And if I was going to draw a hydrograph on the whiteboard to show before there was development, this is what happened during the rainstorm. So this is the before development in its natural state, where we have time on the horizontal axis and runoff on the vertical axis. After development, the peaks are higher and they're sooner. And so the two things that we're doing battle with is that the time to peak is earlier, which is dangerous because now that means on a intensity, duration, frequency curve, we're using a higher intensity value. So remember, it's the time of concentration that determines which rainfall intensity to use. And so for one thing, you're using a higher rainfall intensity, which in part is why the peak itself is higher. And then the other thing is that you have overall more volume that has to be detained because the C value is higher. So it's kind of a double whammy, as they say. Now, inlet control, this is just illustrating that underneath a parking lot you could have storage of the rainfall. And so here's the catch basin, and the catch basin is connected by pipes to these buried tanks that will drain slowly. It may be that they have slotted openings on the bottom, and this is showing it's kind of like a thick gravel bed, and the water would just drain down through that. It may be that when they're full, then the water flows through the pipes towards whatever stream or receiving body is downstream. But we're just trying to give the water some place to temporarily be stored close to where it was generated to try and prevent it from arriving too quickly at some other location downstream. If you're going to build a storage vault, then inline detention is one way to manage stormwater, and that's an approach that's used in a lot of big cities where they will have underground areas. It's something that's done in Japan. I think Chicago has a pretty elaborate inline detention system where it's very expensive because of the cost of concrete, and in some cases, if it's buried really deeply, then you have to pump the water up to get it out of the detention, and that can be costly as well. But it's better than having flooding. The effects of flooding would be far more costly. If you go further downstream, then the flow equalization basins have to get progressively larger and larger. And at a wastewater treatment plant, then a flow equalization basin is important, especially if you have a combined sewer, because remember, the combined sewer is carrying both sewage and rainwater to the same treatment plant. And that means that the microorganisms that are going to be treating the wastewater will have a sudden inflow of a high volume of water during wet weather, and then they're not able to ramp up production as quickly as maybe a chemical process or a physical process. When you're relying on biological conversion of waste into inert products, then it's important to feed the microbiome, bacteria that are inside of a treatment plant at kind of a more steady rate. And so that's why one common place that you'd see flow equalization basins is at a combined sewers wastewater treatment plant. So that's a little bit about the stakes, like why we're so aggressive in trying to reduce the peak of a stormwater runoff curve. Here's some pictures of flooding in West Virginia. And you know, these pictures come from 2009. You could find similar pictures from any year where some community in West Virginia has been really negatively affected by too much water. And in part, it's because of the curse of West Virginia's topography. The fact that the land area is so steep, people generally are going to build on what limited flat area there is, and that's almost always in a floodplain or adjacent to a creek. And so obviously stormwater and rainfall is a really important topic here in the state of West Virginia, and it could be said hydrology is important in wet climates, but it's not just in wet climates. I've lived in extraordinarily dry climates, and hydrology is important there. Here's a picture of Richwood. This is the flood that happened, I think it was 2016. It was kind of a really big flood. You may remember that, was it, what's by the Greenbrier, is that it's White Sulphur Springs? Yeah. I drove through that town. I didn't know that there had been such extensive flooding. I was just driving home from Washington, D.C. and looking for some place to have dinner, and the town was completely shut down. And this was still several weeks after the flooding had occurred. And so there's a lot of damage, both the direct damage of buildings having their foundations affected, or maybe now the drywall has to be replaced, or the city's going to have to remove a bunch of debris from the middle of the roads. That's the direct damage. But the indirect damage is all of the lost revenue from people who are passing through and not spending money when they normally would have, and people who their job is closed for time that it takes to recover, and so they're not getting paid. And so the stakes of flooding can be pretty extensive. Let's take a look at this video that, I don't know, I shouldn't find it amusing, but I do. It's showing what happened when there was some flooding. Let's wait here. So flooding is serious business, and it's also a problem in dry climates when it doesn't rain very often, because they have the mentality, it doesn't rain very often, so it's not important for us to put the infrastructure in place to handle rainwater. But then it does occasionally rain everywhere. These are some photos that I took when I was living in the United Arab Emirates, and you know that there's a lot of water coming out of the mountains just based on the size of the channel that they've used to convey the water out towards the ocean. And this is over on the eastern coast of the United Arab Emirates. But another thing that most people don't realize is that they're going to great lengths to try and trap whatever runoff that they have in a series of groundwater recharge dams. Because in the UAE, about 90% of the drinking water comes from desalination, which is really expensive. The cost of desalinated water is about $1 per cubic meter, whereas the price that we pay for water coming out of the Ohio River would be maybe just a couple of pennies per cubic meter. And so it's really expensive to desalinate water, and so any drop of rainwater that they've got, they'll try and get it to infiltrate. And so you can't see that this dam has been built specifically to trap the rain that comes out of the mountains and the hills to try and get it to go back down into the aquifer. Similar thing here. This is a different location in the UAE where they're attempting to have an increase in the groundwater that's being recharged from surface runoff. This is in the city, and this is not intentional here. This is not a dam that they've put in place, but it's just bad planning. Yeah, it's a lot of the parking lots in downtown areas in the United Arab Emirates are just sand, and you wouldn't think that sand is going to become fully saturated, because the voids are relatively large. The particles don't hold on to water like clay does, but still on a very rainy day even the sandy areas can become fully saturated and the infiltration is low. And so if there's no storm drains to try and draw the water away, then Really expensive cars can get totally flooded, you know, nice Mercedes or a car that's so new it still has plastic over the seats. I don't know if you can see that in the picture, but they'll have a flooded engine but plastic over the seats after this day. People are not accustomed to it being rainy. Here, a garbage bag over the head. I'm not sure if he had a hole to breathe through, but the taxis might have been canoes for as deep as the water was. It was a really rainy day. I was driving around just getting a lot of pictures, and my car never was the same after I drove around that day. I drove through some deep puddles that I shouldn't have driven through. Sometimes in underpass, you know, here in Huntington, let's say going under the railroad tracks at 10th Street, there's a drain there, but if it rains really hard, the drain can't keep up. And so you've probably seen that sometimes they close those underpasses. Unfortunately, a lot of the highway underpasses in the UAE don't even have any drains. And so what they have to do is they have to send trucks out with a vacuum, and they'll fill up these tanks and then drive out into the desert and discharge the rainwater. And so they'll have a line of trucks to just keep pumping out the underpasses, and then because the visibility is bad and the roads are slick, then it's just inevitable that there's going to be accidents. And so you can see that this one's been totally demolished while it was on the job, probably. Another aspect with not having a stormwater infrastructure in place is if you don't have, you know, curbs and gutters and inlets on those curbs and gutters, then you just will have standing water. And that can be a health concern in a warm climate where mosquitoes might breed, and if you just have standing water, then it's ideal for mosquito larvae to grow and diseases like Zika to be transmitted. Down in Florida, they got so paranoid about Zika in particular that even puddles from the condensation off of an air conditioner, the county health inspector was going from street to street looking for standing water, just minor puddles of just a couple of maybe square inches in diameter would be enough. So even in places that are normally dry, and in the UAE they only get about 4 inches of rain per year, compared to here we get about 40 inches of rain per year, so they're only getting 1/10 of the annual rainfall. The thing is that most of that 4 inches of rain will happen on the same day, or maybe spread out over 2 days at most. And so when it rains, it pours, and the place gets really flooded. So remember that what I mentioned at the beginning of class is that so far we've been confining this course to some extensions of hydraulic engineering, with the modeling using HY8 and the rational method design using StormCAD. That's mostly been hydraulic engineering. What we're going to turn to now is more of a focus on the basics of hydrology. And specifically within hydrology, there can be hydrology at the surface, which has to do with the atmospheric cycle and what fraction of the rain will infiltrate versus go over the surface. But then there's also another subdiscipline of hydrology called subsurface hydrology. And there are whole courses that only address the movement of water through the soil. And we'll spend a little bit of time at the end of the semester doing some subsurface hydrology. We'll go through some calculations having to do with pumping water through an aquifer. But for the most part, we'll just focus on surface hydrology this semester. Now, designing a pipe and figuring out how big of a pipe is required is kind of the output of the hydrologic analysis that we do. And so that's the information that the hydraulic engineer is coming up with. And sometimes open channel flow also has some ties to hydrology as well. You know, the HY8 culvert design, you have to understand the capacity of a channel downstream of a culvert, for example, to understand how the culvert itself is going to behave. And so, you know, the water is either going to go into an open pipe, an open channel, or in some cases the pipes are pressurized with runoff from storms. But pipe flow, if it's open to the atmosphere, like if the pipe isn't full all the way to the top, then it behaves as an open channel. Now, the water cycle is the study of how and why the water moves through the environment. And at one point we can trace all of the water that's either underground or on the land surface or in the atmosphere. We can trace it all back to the ocean. And the driving force is the sun's energy. The sun's energy powers the water cycle, and the movement of the water from liquid form in the ocean, where it's saline and not of particular use to us unless we go through a really enormously expensive process of desalinating it. But of course, through the evaporation process, that salt is left behind and only the water molecules will travel through the atmosphere. And then from there, it can go a lot of different places. And this figure that comes from the USGS is pretty interesting because it shows all the different ways that water is getting into the atmosphere and then back out of the atmosphere. You'll notice they even go so far as to identify that some water enters the atmosphere as volcanic steam. The process of sublimation, for instance, is the direct conversion of ice into atmospheric water without it melting first. And so, the more typical thing would be for ice to melt, and then once it's melting, it has enough vapor pressure to be evaporated. But there is a very slight vapor pressure even for ice, so that ice can evaporate into the atmosphere. Evapotranspiration, this arrow, is referring to the effect of plants losing losing moisture through their pores. And so the process of taking water from underground through the roots and then kind of like exhaling water in the same way that we exhale. Every time you breathe out, you're also losing a little bit of water. And so plants do the same thing, and that's a separate process from evaporation. Evaporation is from standing water, but evapotranspiration is the process of vegetative cover losing moisture to the atmosphere. Some of the water that will get onto the surface is going to run on top of the surface back into the ocean. Some of it goes down through the ground, and maybe the groundwater will come back up to the surface before it goes back out to the ocean. You'll notice that in this figure that it differentiates between a spring, which is a pressurized release of water from the ground to the surface, and then water can also travel into a standing freshwater lake through exchange at the underneath the water surface. Rather than being pressurized, it's a much slower process in that case. But this water cycle is really important. The textbook also has kind of a quantitative breakdown of the amount of water that's over the entire over the entire Earth's surface. These are averages. So for instance, if we say that we're going to have 100 units of precipitation onto the land, then in order for that to occur, 100 units of precipitation onto the land, then we have to have 424 units of evaporation from the ocean. And the reason being that since most of the Earth's surface is water, that of that 424 units of evaporation, the majority of it is just going to be precipitated back onto the ocean. And so some of the precipitation that occurs onto the land is coming from moisture that was generated over the land. But this quantitative representation kind of gives you an idea of the relative fraction of the water that's getting back into the ocean from the surface. It's saying here 38 units of surface outflow compared to just 1 unit of groundwater flow. And that's because the speed at which water can move over the surface versus underground is so much greater. The relative quantity of water on the Earth's surface and where it's tied up is kind of interesting. And if we think about all of the water on the planet, 96% of that water is in the ocean, and just a tiny, tiny fraction of the water on Earth is fresh water. 2.5% of the total global water is fresh. And of that fresh water, we're not able to use the majority of it, because the water that's in the glaciers and the ice caps is permanently tied up and bound and far from human civilization and establishments. And even of the groundwater, much of the groundwater is too deep to pump. And so the water that we rely on is mostly groundwater that's less than a kilometer from the Earth's surface, and then surface water, like lakes. And a lot of even the a lot of the water at the surface isn't necessarily usable because it's maybe snow over the land surface, and so we don't generally like scoop that into piles and then try and turn that into drinking water. So like this figure, this series of successive illustrations that what we use rivers, 0.46% of a tiny fraction of a tiny fraction. It kind of gives you an idea that we're really fortunate to live as close as we do to such an abundance of fresh water that's relatively clean, that can be made pretty clean through the treatment that it goes through, and at a relatively good cost. There are a lot of places that don't have access to as much fresh water. So most of the water is inaccessible to humans, but that's not to say that it's not doing something, because even the water that is, there are underground brackish aquifers, and so that's saline water that is similar to groundwater that you maybe could pump out, but it's maybe because of saltwater intrusion from the ocean, it's having a big effect. And so, all of this water that isn't usable for drinking is still important, but the main purpose of this figure is just to illustrate the limits of the water that we can use and how we need to be protective of that resource. The basic unit in hydrology of the watershed is based on the terrain and the ridge lines of a basin, where we're trying to figure out where the water is going to congregate to when it rains. And so just to illustrate that, this is a free program. I don't know if many of you have seen Google Earth Pro before, but here we are in the area by the Huntington Mall. And one of the cool features of Google Earth is that it allows you to visualize the 3D terrain. Let me make sure, yeah, okay, so the terrain is turned on. What that terrain is there's a digital elevation model. It's abbreviated to DEM, where if you move your cursor over the map, you can see down in the bottom right corner it's telling you the elevation at each of these points. And so through either surveys in the olden days or nowadays, they will fly over an area with an aircraft that has a LiDAR, and they get an elevation model. And what you can do is you can tilt down and you can kind of start to see the topography through pivoting. It's easiest to see it if you're moving, and so you can kind of see that here is a basin, and so here's the ridge line, and if water is falling on that area, maybe because of rain, then there's going to be a creek here. And it's not random, and it's not a surprise where the creek is going to be. It's just where is all of the water that falls within this basin going to drain to. There's going to be a low point coming out of that area. And so what we can do is we can quantify that area. Here in Google Earth Pro, one way to do it would be to draw a polygon where you think that watershed area is. And so if we wanted to find out what's the area that contributes to flow at this creek, we could start to draw where on top of the ridge line, and then here in the measurements it would tell us, let's see, the area in acres, so 44 acres. And maybe we didn't click in exactly the right spot. Maybe we could do a better job if we get a good sense of what is the contributing area of this particular watershed. But there are automated ways to do that, and towards the end of the semester you're going to gain access and learn how to use a program called WMS, which will automatically analyze a DEM, a digital elevation model, and it will pick out the ridge line and it'll automatically compute what's the contributing area for a rural watershed like that. But the drainage basin is kind of the basic unit in hydrology, and we can make a nested hierarchy of drainage basins. And a watershed ends at a point of interest. What we're usually interested in is maybe a road is crossing a creek, and so then we want to know how much of an area is upstream of that crossing. Or you could argue that a watershed ends at the ocean, because this would be that little watershed that we were just looking at, but it's within a larger watershed, which is in an even greater one. So the point is that a large watershed is made up of lots of basins that are inside of it, and that's a nested hierarchy. And the amount of water that's going to come out of a watershed depends on the size and the area that's contributing. It depends on what sort of things are in that watershed, whether it's an urban area with lots of pavement, or maybe it would be on the other end of the extreme, a completely undeveloped and undisturbed natural area that has a lot of forest litter that's going to improve infiltration and slow down the movement of water because it has a high delay coefficient. It also depends on what soil you have within a watershed. So if you have well-drained gravel, then maybe that would promote a lot of infiltration compared to if it's a poorly drained plastic soil or clay, then that's going to tend towards a lot more runoff. The terrain and the slope angle, we've talked before about how the runoff C value depends on how steep the land is, and flat land will generally promote more infiltration than sloped land will. And then finally, we have to understand the rainfall intensity to take into account what runoff there's going to be. And so all of these factors play a role, and the models that we're going to be learning how to use later in the semester will approximate the effect of all of these things. We're going to come up with empirical ways of comparing land use that's urbanized versus rural, soil types that are well drained versus poorly drained, the steep terrain versus flat terrain, and we'll try and account for all of these factors to determine what does the runoff hydrograph look like. You know, when it begins to rain, what peak flow rate is going to occur and how quickly does it arrive at the area of interest. Alright, so that's all the time we have for today. Remember that the next thing on your plate for this class is homework 4. I'm going back to my office now and I'll load that online, and it's due a week from today. And of course we're also going to have the quiz on Friday, so let me put that on here, Quiz Friday with the computer. Alright, that's it for today. I'll see you on Wednesday.